discuss fats and lipids. Oops, I need a pen. Fats and lipids. So these two terms are often used interchangeably. Lipids, fats. Technically, I think that the group of chemicals are called lipids, and fats are one of these things that in this group. And there are some other things too, like for instance, there are steroids and things that are also lipids. But people use these two words kind of interchangeably, so you'll often see that. But you should understand that fats are really one group of a bigger class of lipids. So to start this off, I'm going to introduce you to a couple of molecules. And these molecules are also, just remember, all of these molecules are just random assortments of atoms that have found a way to share their outer orbits. So these are random combinations that can happen anytime these atoms get together. So I'm going to draw a little molecule here with 3 C's in it. And then on the top, I'm going to put a double bond O and an oxygen. So that's a carbonyl group. A little OH here and a little OH here. And an H, H, H. So if you had to classify this molecule, what group of chemicals would you put it into? What would be the best way to describe the family that this belongs to? Sorry? Well, it has a hydroxyl. Well, it has not a hydroxyl. You got it. It has a carbonyl group at the top, and so it must be an aldehyde, right? So that's how you would answer that question. This is an aldehyde. And we know it's an aldehyde and not a ketone because the carbonyl group is on the end, not in the middle. So that's the kind of stuff you have to study. It's called glyceraldehyde. 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 And it's a common molecule, and it's a precursor to other molecules. So in biology, it's sort of the small molecules tend to, get reshaped and reformed and built into bigger ones. So I'm only showing it to you because it's an example of an aldehyde. It's a molecule that is very common in biology, and it has a modified version where instead of a carbonyl group on the top, we interact this with something else and we change it to another hydroxyl group. So I just want to show you the difference. That's kind of the idea here. It's a little game of comparison. So I'll put a little line here. Another molecule that looks very much like this one is this molecule with 3 carbons and an OH attached to each of the carbons. This molecule does not have a carbonyl. It has hydroxyls. So which class of molecules would you put this one in? Alcohols. Its name is glycerol. And this is the one that's going to become the formation of the fats and lipids. It's the one we're going to see more often. So I just wanted to point that out. I'm going to see if we can find some good pictures here. And there we go. So glycerol. Technically, glycerol is not really a lipid. It's an alcohol, right? It's a small molecule. But it turns out that we can create fats by, here we go, by taking a glycerol molecule. So I'll draw the molecule again. This time I'm going to draw it a little bit bigger so we have some space. Okay, so here's my glycerol molecule. And you'll notice that it had 3 functional groups, three hydroxyl groups, which form reactive sites, right? Okay, so let's just draw the OHs in. And now what I'm going to draw is another molecule that happens to also be floating around that you can name. And I'm going to draw it like this. I'm going to put H and an O and a C and a double bond O like this. And then I'm going to put some more C's in here. And I'm only going to draw a few because of time, but imagine that this could have as many, well, it could literally have 50, 60, 70 C's in a row. It's a very long-chained hydrocarbon molecule. But we'll just draw it like this for now, nice and small. Okay, and this guy needs H's here as well. What class of molecules does this belong to? Right, it's a carboxylic acid because it has a carboxyl group. And we could name this, if we remember, do you remember the prefix for 5 carbons? Penta. So if it was just an H over here, it would be pentane. But now it's called pentanoic acid. So that's not something I would test you on, but that's for organic chem. Yeah. Yes, it would be an ester if the carboxyl group was in the middle. Correct. Okay, so now here's what's going to happen. We're going to look at, we've got an OH here and an H here. And that can react through what kind of reaction? A dehydration reaction, because that's H2O. Now remember, it's difficult to sort of determine whether it's the OH on this side and the H on that side. I mean, you could also use the H in this OH, and you'd still get the same thing. So it's a little bit confusing. I mean, not confusing. It's a little bit difficult to determine which of those O's is going to be the one that bonds and which is the one that goes into the water. It's possible to do that if we look at relative bond strengths. But for our purposes, we're just going to look at it, and if we can find an H2O in there somewhere, that's good enough for us. So we're not going to worry about the fact that there are 2 possibilities for that to happen, or 2 ways that could happen, right? So we'll just put our OH back and our OH back. And we will say, we'll circle these 2 again, just pretend it's them. And what will happen is, that is a dehydration. So water will come away from there, and it will leave us with a C and this O attached. So it'll leave us with this O attached to this C, like this. Right? So now what I'm going to do is go down and draw the picture again and show them how they would be bonded. So we'll jump down a little bit. Go. So we'll draw a line to keep it straight, and we'll draw our glycerol one more time. So 3 C's, H's on one side, and on the top and the bottom, and the OH's here and here. Now this one, however, is going to be bonded to the C with the double bond O, and then the C, 2, 3, 4, 1, 5. There it is. There's our 5 carbon. And of course, the hydrogens will still all be up here and here. They haven't changed. So we have the carboxylic acid attached to the glycerol. Yes. Oh, yeah, there is. Good question. Good point. Thank you for correcting me. There, we missed an O in here. So let's put the O. All that talk about the O, and then we left it out. You still need to have that carboxyl group showing in there. So this is an ester linkage. It's linked as an ester linkage, right? The C double bond O, O. Okay, so that's actually the correct picture. Very good. What do we call this? Well, this is now called a lipid. It's a lipid molecule. And it has a particular name. Because it's formed from glycerol, we use that in its name. And because it has 1 attached carboxylic acid, we call this a monoglyceride. Where have you heard the word glycerides before? Maybe you haven't heard it too, whoops, not glycerides. Maybe you haven't heard it too much because you're young, but people like me who get older and have to go to the doctor and worry about things like blood cholesterol levels and fats and all of our diet and keeping in shape. We hear about glycerides in our blood. They actually do tests to measure the levels of glycerides because these are fats, and fats, of course, can contribute to certain health issues if you have too much of them, right? Monoglyceride. Mono means one, and it has one chain, right? Monoglyceride. Now, of course, you can see that there are two other groups here where I could do another attachment. So I could still attach two more carboxylic acids in the exact same way. So if I attach two of them, what do you think it would be called? Right. If there are two acids, you would get a diglyceride. And if you had three of them, guess what? Three of them, all three would be a triglyceride. So there's those three different names, mono, di, and tri. And it all depends on how many acids are attached, 1, 2, or 3, because there are 3 sites. So far, so good? Okay. Now we have to talk about the concept of what we call a saturated fat versus an unsaturated fat. Because this is something that's also in the news a lot, right? Apparently, saturated fats are not as good for you. And I should cross my T's because it's not salurated. There we go, saturated fats. So what does this mean? Well, it turns out that if we look at the carboxylic acids that are attached, there's a couple of ways they can form, all right? So let me just draw another couple of pictures. I will draw our little glycerol again, because you know what, the more we draw it, the more we remember it. So let's draw them again. I kind of feel like Bob Ross. There's a happy little molecule, right? And in your world, this molecule can live here just like that. Right. Okay, so we'll put some more C's here. Now remember, these C's, I used pentanoic acid, which is possible, but quite often we have these incredibly long chains, which are called gigantic names, and these carboxylic acids. So I'm going to put dot, 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 and then I'm going to put the one on the end to show us, or to remind us that these can be long, like 30, 40, 50 carbons, not uncommon, right? So there we go. Okay. Now, typically, these other carbons in the chain are all surrounded by hydrogens, right? So that means that each hydrogen, or each carbon, I mean, is sharing with hydrogens like this. And so what that basically means is this chain has the most amount of hydrogens you possibly could get. The most amount of it, of something, means you are saturated with it. You're saturated with hydrogens. So we call this a saturated fat or lipid. Okay? And the reason is because we have all the hydrogens we possibly can get on the carboxylic acid chain. But watch what happens if instead of single bonds, there happen to be some double bonds between the carbons, which is possible too. So let's redraw another picture. Let's draw our little happy glycerol. It's just happy. There we go. You can do it in black or red, whatever color you like. It's your imagination. Let's put our little C here. Nope, let's put our O first. Did I forget the O last time? No, I had the O in there last time, I hope. Let me go check. Yeah, the O's there, good. For some reason, I have this mental block when it comes to O's, like in glucose. All right, so put some more C's here. I'm going to put a double bonded C in there. And then another C. Maybe I'll put 2 double bonded C's for fun, right? I could even have a triple bonded C, I suppose. Why don't I put a triple bonded C in there? Now remember, we're drawing it all in a straight line, but these C's would be bent. They would make this particular chain of carbon atoms bent, and that would change its chemistry. So this kind of a molecule would act differently than the saturated one. Okay, so now when we go to put our H's in, remember, carbon only has 4 hands, right? So this one would get an H and an H. Oh, I guess I should finish Mr. Glycerol here too. I didn't finish him on the last picture either. Look at that. We got so carried away that we went up here. Look at this. And I forgot these little OHs here, so we forgot to finish him off. And then he wouldn't feel very happy. He'd feel it's kind of like being in the mall in your underwear. You're just not quite comfortable, you know? So we finish him off. Okay, let's go back here. This carbon, it's next, has 3 bonds already, so there's only going to be a spot for 1 more H. And the same is true for this next carbon. There's only a spot for 1 more H, and it would probably be on the other side because of Vesper theory, so I'll put 1 on top and 1 on the bottom. And then this one already has 4. And this other one, which is bonded to the next carbon there in the chain, already has 4. So that means that it wouldn't need any hydrogens at all. So what we see is where there used to be a hydrogen in these positions, the double bonds and triple bonds mean that there aren't any hydrogen spots available. So there is not the full maximum amount of hydrogen that you can get. And so this is an unsaturated fat or lipid. Unsaturated. So far, so good? So that's the difference in those 2 terms. And so why is it important? Because saturated fats without double bonds tend to be long chains, whereas unsaturated fats who have some double and triple bonds tend to be bent or kinky chains. And bent or kinky chains have different shapes and act differently in your bodies. So in humans, it turns out that unsaturated fats are less likely to induce the production of low-density lipoproteins, which carry cholesterol from your liver out into your bloodstream, right? Cholesterol, we're going to see cholesterol soon too. It's a lipid, and it's a very important lipid because it's a precursor to so many important molecules. But apparently, if you get too much of it in your bloodstream, it can collect on your arteries and cause these plaques to form, right? And so we find that in our research, at least, it seems that unsaturated fats don't encourage the production of LDLs, low-density lipoproteins, and to carry this cholesterol out. Instead, they tend to promote the production of high-density lipoproteins whose job it is to carry cholesterol from the blood back to the liver. And the liver breaks it up and uses it for other stuff. So there's a complex dance that your liver does balancing these 2 molecules. And of course, the saturated and unsaturated fats play a role in influencing it. Question? Correct, because carbon can only have four hands to hold, right? It only joins 4 times. Question? Go ahead. Like the H's, whether they go on the top or the bottom, that's a little bit more complicated organic chemistry than we need to worry about. But there is a way to make that happen. When things are on the same side, we use a prefix called cis, and when they're on the opposite side, we use a prefix called trans, so we can differentiate between them. And of course, depending on the shape of the molecule and the Vesper theory, the different shapes are possible, but we don't want to get into too much of that detail. Okay, now what's interesting about these fats is their behaviors change, as I said. And so with saturated fats, or lipids, right? They tend to have low. Well, no. Let me start. They tend to be solid at room temperature. That's an easier way to say it. They tend to be, right? They're solid at room temperature. Whereas unsaturated fats tend to be liquid at room temperature. At room temp. And so you'll find saturated fats, things like butter. Butter tends to be a chunky solid. It's essentially a whole bunch of fat. But oil, olive oil, which is a fat made by olives, tends to be a liquid. And what we find is that animals tend to store fats as saturated fats, and plants tend to store it as more liquids and oils. So we find saturated fats in both. It's not that they don't exist, but there is a predominant majority of fats in animals that are saturated. If you take human fat, it's like butter. It's a chunky goo. Whereas if you take the fat out of a peanut, which you can do by taking a paper towel and just taking a peanut at home, putting it in the paper towel and squeezing it, you'll see that the towel will become oily and greasy. And that's because there's oil that comes out of there. In fact, the way we make cooking oil is we take different things like canola seeds, canola oil, different vegetables, whatever, plants that produce oils, and we squish them. And we squeeze out the oil, collect it, put it in a jar, and use it to cook with, right? So plants are producing these unsaturated sort of fats. Yeah, I don't think there's really much else we need to. Yeah, we should say this. We should say that because fats are. Think about butter. If you melt butter, if you warm it up a little bit, it gets gooier, right? And slipperier. But if you let it sit like right now where it's getting cold, it'll get into a fairly hard solid. So what's interesting is if you think about humans, we are made of saturated fats, but if we get too cold, our fats will solid up too much. Right? There's a reason. One of the reasons why we need to maintain a homeostatic temperature of 98.6 degrees Fahrenheit is to make sure that our fats are just the right amount of mushy. If we get too cold, we become just like butter. We would freeze up. And if we get too hot, our fat would melt, just like butter. So our body temperatures are idealized for the saturated fats that we have to keep them just the right amount of gooey, because you want them to be a little bit gooey, but not a lot. There's a question. Yeah, oils. Coconut oil. Yeah, so again, those are generalizations. It's not like true for every single one. The vast majority of fats. Well, coconut oil, it can be a solid, but it's sort of like, okay, so everything has its own melting and boiling point. So what that means is essentially unsaturated fats tend to have much lower melting points. Right? They melt at room temperature into oils. Now there's a wide range. So some of the unsaturated fats produced by some plants will be at the far end of that range where they're almost like a saturated fat, like coconut oil, right? So it's kind of like just a range of temperatures. And we draw these arbitrary lines to sort of say, oh, look, these are the unsaturated, these are the oils, these are the butters or the fats, the solids, whatever. Lard is another example of a saturated fat that's more of a solid, right? You can you can cut it with a knife, but you can't cut peanut oil with a knife. It's an oil. So that's an interesting thing about fats too. Besides the fact that their chemistry changes in the body as well. So they have different chemistry because of their shape. In fact, I'm going to write that. Different chemistry or different shapes mean different chemistry. Because that's kind of the theme, right? The theme of our introduction here to this is that it's all about shape. And the shape determines the behavior. Okay, so we can have a monoglyceride, a triglyceride, a diglyceride. Here's another thing that can happen to these cool lipid molecules. Let me get a picture of this just to make sure that we don't... I had a picture ready to go here. Yeah. Watch this. We take the glycerol. So C, C, C. And then I'm going to draw in the bottom two. And we stick on two, sort of, that's kind of stuck together there, but we don't have to worry about it. Put the long chains in here, dot, 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 and the end. Could have made this a little bit bigger. And of course, you could have a double bond here, which would actually cause the molecule to bend. So here I'll show the bend this time, just to remind us of that. And there's a kinky one and a straight one. And you can imagine all the different sort of variations of that. And then the hydrogens, I'm going to grab a thinner line here and just try and squeeze those in small. There we go, hydrogens all around, and then I have to squeeze them in on this one too, so it's going to get a little bit crazy. Careful here, because the double bond means that there can only be one hydrogen on those guys, because he's unsaturated. There we go. Now, the other OH at the top, something cool can happen. Instead of bonding itself to another carboxylic acid to turn this diglyceride into a triglyceride, and remember that these bonds can rotate and spin, right? It tends to spin around the other way. I'll go back to my regular line thickness here. It tends to spin around the other way and attach to something else. It attaches to a phosphate. So let's put that on here. And it attaches like this. It attaches with an O here. And I'm just going to kind of draw it sort of... yeah, I guess that'll work that way. So we'll put the P on here, and then we'll put the double O here, and we'll put the other O here. And then there's another molecule up here, which I'm actually not even going to draw. Well, I guess it's kind of supposed to be on there, so I'm going to have to erase a little bit of this so I have some room. And this molecule, it doesn't really matter why it's there, what's going on, but we're going to put a little C here with an H2 on it. We'll do the shortcut version. So that's two C's coming off, and then another CH2 up here, and then bonded to that is this little weird nitrogen atom, and then it's got 3 CH3 groups all sort of stuck around it like this, so it looks like that. Well, we don't have to worry about that part of what that's called. It's actually called a choline. This is a choline molecule. We'll worry about it. But this part, the other O goes here, and the other H's go here, and there should be another H here, and an H here. So what we've done is we've added this phosphate group and this choline. I'll write that down for you in case you're interested. Choline, and we've added the phosphate up here. This molecule is called a phospholipid, because it has the phosphate attached, which changes its chemistry a little bit as well. And the reason I'm putting this up here is because this is a very important lipid. These phospholipids are actually the building blocks of cell membranes. You may have learned about the phospholipid bilayer that forms the fluid mosaic model of a cell membrane. And so what we do is we do a shortcut. Instead of drawing these huge big molecules, let me just go up a little bit there for a second. Instead of drawing these huge big molecules, we take this part, which is sort of like the head, and then we have these two long tails that stick out like this, and sometimes they're bent or straight. And so we just simply draw this as a simple shape, but we have to understand what it is. When you learned about the fluid mosaic model, you may have drawn these little guys, right? These little molecules. And you might have said, oh yeah, those are phospholipids, and now you understand exactly what they are. Here's the interesting thing, though. And again, the water dance is coming back. The interesting thing is, look at all the oxygen in the head, the big circle. Look at all the oxygen molecules on this side of the molecule. Oxygen is an electron hog. And what this means is that this side of the molecule, you'll notice that there's more oxygens on one side than the other. My picture's getting crazy, but there's way more oxygens over here, right? And there's oxygens on this phosphate. And what this does is it creates a polar nature to the head of this. Those oxygens are causing an uneven distribution of electrons. So the head of this is highly polar because of all those oxygens pulling the electrons. But the tails are pretty much oxygen-free. Well, they are. And they're pretty much symmetrical around the carbons. And so there's really no polarity there at all. So the tails tend to be nonpolar. And remember, because the tails are so long, 35, 45 carbons in a row, the tails are quite a ways away from the polar part of this molecule. So what we have is a molecule that has a sort of a little bit of a bipolar personality. It's interesting we use that same word. We have a molecule that has a polar end, which I can just put a plus and minus over here, and then it has a non-polar end. This long part over here, I'll put NP, non-polar. Now remember, water is polar. Water likes to push and pull on things that are polar. So water will be all excited about the head part of this molecule. And when it goes in the water, water will love to surround this head, attracted to the pluses and the minuses, the water dance. But the water will be kind of mildly indifferent to the tails because there's really nothing to attract to. Non-polar substances don't dissolve in water very well. So we have a molecule where half of it likes the water. We call this end the hydrophilic end, and the other end is called the hydrophobic end. It's afraid of the water. Not really afraid, but it's basically just, it doesn't prefer to be in water. It doesn't stay in water very well. It would rather hang out with other non-polar molecules. So now watch what happens. I want you to remember, you take a bunch of O's and H's and C's, you put them in a cup and you shake them, and you get a million different combinations. One of those combinations would be the phospholipid that we just drew, randomly, because the atoms will get it together, share their outer orbits, share their electrons, do that. They just make it. They just bloop, and there it is. Now, if this is in the water, and this happens, what happens to this molecule when he's in the water? He starts to feel weird. The hydrophilic head part wants to stay in the water, but the hydrophobic tails prefer to not associate with water. And so immediately, once they're formed, they begin to group together and form little blobs like this. Because the tails are like, screw the water. We want to get away from the water. Now imagine this is like a sphere. They form a spherical blob where all the tails point inwards, so they're sort of out of the water, and all the heads point outwards. So this is where all the water is, out here, right? And everybody's happy. So when you do the dishes at home, most of us have a dishwasher now, but when you're scrubbing those pots and pans, you might have noticed that if you try to scrub, like Thanksgiving, you got 12 pots to watch, and you're scrubbing the pots and pans, you might have noticed that if you didn't put enough dish soap in, that after a while you start getting little blobs of grease in the water. Have you ever seen that? Those little blobs of grease are these. They are fat molecules that have formed into blobs because of the polar nature of them, of the heads, and the non-polar nature of the tails trying to get away from the water. And it all just happens because of the water properties, the polar nature of water. Now, why is this important? Well, because there are many ways that these atoms can arrange themselves to get out of the water. Here's another thing they can do. They could sort of float to the surface of the water, these phospholipids, and stick their tails right up in the air. Here's the water. And they could form like a scum or a layer, which we have also seen fat in our dishwater do. When fats float on the surface of water, this is what they're doing. Those non-polar tails are trying to get away from the water, but the polar heads are quite happy in there. Watch this now. Another way that they could preserve this weird bipolar nature is for them to get together on the surface, or on the surface of the water, I guess you could say, like this. They could point their tails downwards, like this. And then another group could get underneath and point their tails upwards, like this. So what you've got now is a bilayer of phospholipids where the inside part is protected from the water, doesn't like it, and the water is only touching the outside parts, the hydrophilic heads. Now I want you to imagine that this bilayer of stuff is floating on the water back millions and millions and millions, literally billions of years ago. And it's floating on the water, and there are the ancient oceans, what we call the primordial sea. It wasn't like Lake Superior. It wasn't nice and fresh and clean. It was full of all these molecules that were just forming randomly as they share, interacting, right? It's a soup of goo. And in this water, these guys are floating on the top. And now the waves are washing up against the shore. Whoosh, whoosh. And what do you notice when you go to the lake sometimes? What do you see where the waves are washing up on the shore sometimes? Foam. What is there foam? There are foam because the fats enable the water to take little bubble shapes. So what happens is a bubble forms. A bubble forms in the water due to the wave action swirling this around. Okay? I'm going to just go faster here to make this faster. Here's the heads of all those phospholipids. And here's the other layer on the inside. And it turns that flat layer into a round bubble shape. Now remember, this is a sphere. It's not a circle on the board. It's a full spherical bubble shape. And then when the bubble sort of pops, it leaves behind this round sphere-shaped blob of fats. Well, now you definitely have an inside and an outside that have formed. You've created a barrier between two different environments just by random things happening. And this, of course, is the primitive cell membrane. You can kind of see now how a cell membrane might have evolved or might have came about because of these natural processes. So we've been able to take ourselves from the world of atoms and see how the atoms make these complex molecules which have interesting behaviors because of their shapes. And those behaviors then have now taken us to the level of the cell. We now understand what a cell membrane is. It's a bunch of those phospholipid molecules, carbons, hydrogens, and oxygens, doing their thing simply because of the way the electrons are distributed, the polar nature, and the good old water dance that makes it happen, right? Then you can imagine, if you take the story further, you can imagine that when this layer formed, perhaps a big chunky protein got sort of stuck in there, and maybe one over here. And other molecules got sort of stuck into the membrane. And you can imagine how over literally millions of years, different combinations of membranes would form and break and form and break. And each time they would be maybe a little more complicated, and all of the interesting functions that they do would come about simply because of the way these molecules behave in the water. The water dance is responsible, in some part at least, for the formation of the building blocks of life. That simple fact that water is a polar molecule. That's how important that is. Okay, so the phospholipid is a very important form of lipids too. It typically, in membranes, a diglyceride. But you could have monos and surprised as well, but I think this is, with the addition of the phosphate and the choline, this is more of a stable form. So we see these phospholipids, usually with two tails. Okay, any questions about that? One other thing we should talk about are steroids, which are lipid molecules. We're not going to get too crazy drawing pictures of steroids because they're quite complex. I'm going to show you one for fun. Now, when we get into these complex molecules, do you have to memorize them? No. I'm not going to make you draw them from scratch. But here's what I would like you to do. I'd like you to be able to recognize them if you saw them. So you can kind of look at, they all have sort of telltale signs that help you identify them, all right? So I'm going to draw you a lipid molecule. I'll draw it in a nice purple color for fun, okay? And after we draw this molecule, we'll take a little break. Well, it's 9:30. Yeah, after we finish this, we'll take a little break. Okay, so I'm going to use the shortcut that every corner is a carbon. So imagine a hexagon ring of carbons like this. Those are all carbon atoms at every corner. Then imagine another hexagon ring joined to it. So these are big, okay? Then, I'm going to have to go up a little bit. Then, imagine another hexagon ring right over here. Okay, so far so good. So 3 hexagon rings, and then a pentagon ring. Right there. Then, attached to the top of this, there's a chain of carbons. And each corner is a carbon atom. So I'm going to put a little black dot. There's a carbon atom. Black dot. Nope, my smart board's being silly. Black dot. There's a carbon atom right there. There's a carbon atom right there, right there, right there, right there. And at all the corners of these, okay, I won't do them all, but that's what we're remembering. Okay? And then this is attached to, let's see, we've got an H3C on this end. Over here we have a CH3 and a CH3. Those are all 3 of the same thing. One's just written backwards. So those are called little methyl groups, kind of. What else do we have? Oh, there's another CH3 right here, in the middle there. There's another one sort of sitting in the middle here, and then there's a little OH stuck off to the side here. HO. So this is a huge molecule too, and it's quite complicated. And aside from the sugars, this is the one that has all these rings in it. We haven't seen too many rings aside basically the sugars that we saw, and now this one. Guess what his name is? Cholesterol. Cholesterol. And he's a steroid. There are other steroids. Well, what you can do from cholesterol is, because it has a ring structure, we can turn it into something else. So this cholesterol could be adapted. I'm going to leave that there for a second because you guys probably haven't finished it yet. So I'm going to pause the video while you copy that. All right. So I've drawn a line here because we're going to draw 2 more. And these 2 are 2 steroids that are made from the building block of cholesterol. So you start with cholesterol, and then we draw these 2 crazy ones just for fun. And you'll see how they are very similarly related to the cholesterol molecule. So they both have, here's the first one. Maybe I can draw them a little smaller. They both have the same general hexagon, right? And then hexagon, all of carbon. And then hexagon, and then pentagon. So they have that same basic shape. The only thing that's different is, I have to erase, the only thing that's different is the little things that are stuck to it. I'm going to erase this line. I've got to go up here a bit. I didn't leave enough room. Hopefully you did. So we basically just change the sticky things on the outside. In this molecule, there's an OH here. The long chainy thing has been kind of pulled off. There's a CH3 here. There's a CH3 here. And the little OH has been demoted. The H has been kicked off, and a double bond oxygen has formed down there. So you can see how closely related that is to cholesterol. It's basically just chop off that big chunk at the top, change a couple little things, and we have this steroid, which is called testosterone. Very important steroid hormone. It's a hormone because it also has an additional function. Besides being a steroid, it does stuff to our bodies. It messages and changes the way other things react. In fact, what testosterone essentially does is it makes you a boy, right? So when you are an infant, when you are not even an infant, when you are just a little blob of cells, essentially, probably the very beginning stages of an embryo, maybe not even yet, there are genes inside of you, if you have a Y chromosome, that will suddenly turn on and start working. And what they do is they are the instructions for making this molecule. And so suddenly this testosterone starts to build up in the system, in this ball of cells. And what it does is it affects the way cells grow. And so it turns things into boy parts, believe it or not. So everybody's kind of like a girl at first. And then you get a little shot of testosterone, and that causes your parts to grow into different things. Girl parts and boy parts are actually derived from the same tissues, except that with testosterone, they shape themselves into boy things, and without testosterone, they grow into girl things. Penises and vaginas, essentially, right? And so that's a very important molecule. So because of the Y chromosome, men tend to have lots more testosterone in their system than women. Women don't have a Y chromosome. They have some testosterone, but not very much. The other one, then, not to be outdone by the boys, is this one, which we'll draw a line here. And this time I'll leave a little extra space. Were you done that one? Okay. So the same idea. I'm going to draw a hexagon, attached to a hexagon, attached to another hexagon. Whoops, went the wrong way on there. Let me fix that. Another hexagon. So now you can see how easy it is to start, and then a pentagon, to start recognizing. If you see 3 hexagons in a pentagon like this, you pretty much know it's a steroid, right? You can be pretty safe at guessing that, at least with the molecules that we're going to be using. Okay, I'll bring it down a bit. This one has a couple other little additions. Instead of the OH right here, it has a C, double bond O, and a CH2. Oh, CH3, my mistake. Obviously. Oh, I hate when it does that. It jumps up. I don't know why it's doing that. Eraser, CH. Maybe I'm hitting too hard and it's just 3. Then it has a little CH3 in the middle. These don't change. You'll notice these are always there. And the little double bond O down here. So it's very similar to testosterone, isn't it? In fact, the only difference is this top piece. That little bit is all it takes to make this a different one called progesterone. I think is it progesterone or, yeah, it's progesterone, right? Progesterone is a female hormone. You can also make estrogen from these. We can make 1,000 things, so we'll not go into them all. I'm just showing you 2 examples because these are very similar. And of course, progesterone is a very important steroid because in females it helps regulate the menstrual cycle, right? And so essentially, what happens is when you ovulate, a little egg comes out and down it goes to fallopian tubes, and it makes its way to the to the uterus. And when it implants in the uterus, if it's fertilized, the uterus will produce progesterone because of that implantation, and the progesterone moves through your body, and when it goes to the ovaries, it says, no more eggs, please, for a while because we're busy. And so for the next 9 months, while that egg is growing into a baby, you don't make any more eggs. And so your monthly cycle sort of grinds to a halt while you're pregnant. And we learned, of course, that, well, heck, what if you're not pregnant and you just take a pill of progesterone? Well, then that pill goes into your bloodstream, and that progesterone goes to your ovaries, and it says the same thing. It says, hey, not right now, we're busy. But we're not really busy. So we fool the ovaries into thinking we're pregnant by taking the pill, which means no ovaries or no eggs are being released. And so this is a good form of birth control. Anyway, that's one of the things that progesterone does. So those are the steroids. Okay? Now, steroids are divided into two sort of groups. So I'll just put that down. There's two major groups of steroids. One are the water-soluble steroids, which means they dissolve in water easily because they have polar natures around them. They have polar parts and pieces that water likes. And the other one, of course, would be the fat-soluble steroids. Fat-soluble. And we're not going to get into a whole bunch of details on this yet. As we talk about steroids later, we'll notice that this makes them have two very important functions. If you want to float around in the water, that's great. But if you want to get inside a cell, you've got to pass through the lipid bilayer. And to do that, you have to be fat soluble. So if a steroid needs to get inside a cell to do its job, then it tends to have to be fat soluble to get through the membranes. If it's water soluble, it'll stay on the outside. Now you can still mess with cells on the outside because cell membranes have all those sticky out molecules, right? The polysaccharide glyco things that are all sticking out like little branches. And so molecules can interact with those and they can change the nature of the membrane and affect how a cell works. So basically, you have water-soluble steroids that are sort of outside cell workers or messengers, and fat-soluble ones that can sort of squeeze into the membrane. So that's kind of why that's important. But that's all we'll say about that for now. And that ends our discussion about lipids and fats and steroids.